Hey guys, my name is IBM, and in lesson 5, I think this is going to be lesson 5, and this is going to be the last lesson. And I think lesson 5 is going to concentrate on equilibrium, which includes equilibrium along an inclined plane, equilibrium of suspended objects, and so on and so forth, or equilibrium of involving ladder problems. That is basically what is going to be in lesson 5, and I hope it is going to be very, very short. Okay, so let us start with equilibrium along an inclined plane. So let's consider an object at equilibrium. We are talking about equilibrium. In one example in lesson, I think 2, we talked about objects on an inclined plane, and we explored the forces which act on the object. So in equilibrium, we shall just concentrate on the object being at equilibrium. So of course, there are two conditions for a body to be in equilibrium. The resultant force must be 0. And of course, the resultant moment is going to be 0. So here we shall just consider at the resultant force being 0, which means the acceleration is also going to be 0. So an object is only in equilibrium. If it is moving, it must be moving at a constant speed where the acceleration will be 0, or it should be at rest, where in all cases still the acceleration will be 0 because the resultant force should be 0. So in that case, we talked about the forces which are acting. The forces on the object, we have the normal force which acts at 90 degrees to the surface, or the normal reaction force. And if this angle is theta, remember we derived the angle here and it was also theta. And we said if we can resolve mg perpendicular to the surface, and it is mg cos theta, elsewhere it is going to be mg sin theta. I said if the angle is between the vector and the direction you want to resolve to, that is always cos. And if the angle is between the vector is not between the vector and the direction you want to resolve to, it is always going to be sine. So the normal force exerted on the body by the plane, that is perpendicular to the plane. The normal force N exerted by the on the body by the plane, that one acts at 90 degrees to the plane. Then we also have the force due to gravity, which is the weight acting vertically downwards. But of course, parallel to the plane, just a component of the weight acts parallel to the plane, and it's the component of the weight which is responsible for balancing the force upwards if our friction is ignored. Then we also have to consider the friction in case the surface is not smooth. So the frictional force F acting parallel to the plane, in a case tendency of motion is most likely going to be downwards, so the frictional force must be up the plane to balance the component of the weight down the plane, which is most likely going to make the object move down the plane. So the frictional force will act upwards if the body tends to slope down the plane. Alternatively, it can also act downwards if there is a force moving the body upwards. So the friction force will always act along the plane, either upwards or downwards. It is downwards if there is a force pulling the object upwards, and it is upwards if the object tends to slope downwards, because friction always tends to act in a direction such as to oppose relative motion. So in equilibrium, the force up the plane is going to be equal to the force down the plane. So if friction is up the plane, That means the frictional force F is going to be equal to mg sine theta. I want to use a small letter F for frictional force. Is going to be equal to mg sine theta. In equilibrium, the normal reaction N, which acts at 90 degrees to the surface, is going to be equal to mg cos theta. That is if there is equilibrium. So we are still exploring equilibrium along an inclined plane where we have now seen the forces which act. So W, like I have mentioned, the weight W has a component along the plane, which I said it is going to be mg sine theta. We can choose along the plane to be the x-axis many times and the perpendicular to the plane to be the y-axis. So it is as simple as traversing these planes by rotating this through so that it looks like this, where in the horizontal, the angle we are talking about will be somewhere here, because this is in the vertical, that is where we had the weight mg, and the angle we are talking about, I think theta is going to be, sorry, we rotated this, so mg comes somewhere here, mg comes somewhere here when we rotate the axis, and this becomes a theta. So when we take this to the vertical, it becomes mg cos theta. When we take it to the horizontal, it becomes mg sine theta. So we choose along the plane to be the x-axis, and the perpendicular to the plane to be to act like the y-axis. Thus, the component of the weight along the plane is mg sine theta, and the component of the and the perpendicular to the plane is going to be mg cos theta. So when we resolve the weight parallel to the plane, it is mg sine theta, and the perpendicular to the plane is mg cos theta. And since there is no movement in the vertical, there is no movement perpendicular to the plane, it means that the normal reaction always balances mg cos theta. And if the component of the weight parallel to the plane is greater than the frictional force, then it means the object will slide downwards. Of course, if the frictional force is greater than the component of the weight, then the object may slide downwards, but still at a smaller acceleration or at a negative acceleration. And also, if the two are balanced, mg sine theta is the same as the frictional force, then the object may remain stationary on the plane. Therefore, we say it is in equilibrium. So, if the component of the weight part of the plane is greater than the friction, then the object will of course slide down the inclined plane with an acceleration which will depend on the resultant force along the plane. And when the angle theta, or when the angle of the slope is zero, sine theta is also going to be zero, so the body will not move. So if theta goes to zero, we notice that sine theta is going to be sine of zero. If theta is going to be zero, it means the surface is going to be horizontal. The plane is no longer there. So the surface is horizontal. And if the surface is horizontal, it means the body will just remain in one place. So the body will be stationary. So that is what we mean by equilibrium along an inclined plane. So the best way to understand this is by doing an example so that we know what we are really talking about. So let's consider a simple example like this one. A puzzle of mass 500 grams rests on a sloping plank. The friction between the surface is 2 newtons. If the slope of the plank is gradually increased, at what angle of slope? At what angle of slope will the puzzle begin to slide? So I can try to sketch this. Let's sketch the slope. So let the angle which is not known be theta, and we're going to have a puzzle somewhere here. And I will indicate the forces which are acting on this puzzle. Let me change the color to red. The weight acts vertically downwards. And they say the friction between the surface is 2 newtons. If the slope of the plank is going to increase, at what angle of the slope will the puzzle begin to slide? So there's a force which is going to be acting on the puzzle downwards, but there's a friction which acts between the puzzle and the surface, which is vertically upwards. And the frictional force is given as 2 newtons. Of course, there's a normal reaction force which acts on the parcel at 90 degrees. That is the normal reaction force. This is the weight of the parcel, which is m times g. Because the mass is 500 grams, 500 grams is, I think, 0.5 kilograms. So the force here is, the weight here is going to be 0.5 times acceleration due to gravity. So the plank is raised until an angle theta where the parcel just begins to slope. Where it just begins to slope. That means before it starts sloping, then there is equilibrium. So at equilibrium, then the frictional force is going to be called the component of the weight which acts down the slope. So remember, the component perpendicular to the slope is mg cos of the angle theta, because this angle is theta. And then elsewhere it is mg sine theta. So if we consider equilibrium, therefore the frictional force is going to be equal to mg sine of the angle theta. So the frictional force is 2 newtons. Is going to be mg, which is 0.5 times g, which is 9.81, then sine of the angle theta. So it means theta or sine theta is going to be equal to 2 divided by 0.5 times 9.81. So theta is going to be the sine inverse of 2 divided by 0.5 times 9.81. So that is theta. So if I press the calculator to find theta, let me try to press my calculator. So 2 divided by 0.5 times 9.81. Sine inverse of the answer. So this gives us theta as 24.1 degrees. So it means if the angle exceeds, I'll round off this to 24 degrees. So if the angle increases beyond this, then the parcel is just going to slide. So the question is, if the slope of the plank is gradually increased, at what angle of slope will the parcel begin to slide? So because I've already rounded off 24 degrees, so if the angle goes beyond this, it will start sliding. So that is how we use the concepts of equilibrium along the plane that I've just talked about above. Okay, and I think that is clear. Let's see if there is another example. A body of mass 8 kilograms is released from rest on the surface of a plane. If the resistance to motion is acting up the plane and the slope of the plane is 20 degrees to the horizontal, calculate the acceleration of the body down the plane and the speed acquired in 5 seconds after the release if the resistance to the motion is 1 Newton. So I'll sketch the diagram here for simplicity. Many times in the exam, the diagram is normally sketched, or the diagram is always shown in the exam. So we have a body of mass 8 kilograms. So I will put a body here. On the surface, so it is a mass of 8 kilograms, so the weight becomes 8 divided by g. And remember, the weight acts vertically downwards, so I'll draw a vertical line for the weight. So it is 8 times g. And the angle and the slope of the plane is 20 degrees, so this angle is 20 degrees. Calculate the acceleration of the body down the plane. So that means there is a resultant force down the plane. So the acceleration is down the plane. And the speed acquired in 5 seconds. So the time is 5 seconds. We want to find the speed and the acceleration. After the release, if the resistance to the motion is 1 Newton, so there is a resistance. I will change the color to indicate the resistance. So there is resistance in the motion, which could be friction or air resistance, whatever it is, upwards. So we can first of all resolve these forces. The weight, there's a force, the normal reaction acting in that direction. which is balanced by the component of 8 newtons perpendicular to the surface. Remember, this angle is 20 degrees. So this is going to be 8g cos of 20. And then there's a component of the weight part of the plane is the one responsible for contributing to the motion down the plane, not the whole 8g. So this is going to be 8g sine of 20. So the resultant of 8g sine 20 and F is the resultant force, which is going to be given or interpreted by Newton's second law. So the resultant force capital F is going to be equal to 8g sine of 20 minus the frictional force. Remember, the resultant force is given by Newton's second law, so I will say M times A is equal to 8g sine of 20 minus the frictional force, which is going to be 1 Newton. Remember, the mass is 8 times A is equal to 8 times G, which is 9.81 sine of 20 minus 1. So the acceleration is going to be, of course, 8 cancels out. No, it doesn't, because I'm going to divide. So that is 8 times 9.81 sine of 20 minus 1 divided by 8. So this gives us 8 times 9.81 sine of 20, then minus 1 divided by 8. So this is giving me the acceleration to be 3.23 meters per second. So that is the acceleration, and then they want us to find the velocity after 5 seconds. So if it starts from rest, it means initial velocity is equal to 0. So initial velocity is equal to 0 because it starts from rest. The acceleration, we have got it as 3.23 meters per second. And we want to find the final velocity. So if we assume that the acceleration is constant, then we can use equations of motion, such as you could use v equals to u plus at, since we have the time. So we can say v is equal to u, which is 0, plus a, which is 3.23, then times t, which is 5. So I will multiply this answer by 5 from my calculator. I'm getting this as 16.2 meters per second. Oh, by the way, acceleration is in meters per second squared, not meters per second. Okay, so that is going to be our speed in this case. So that is equilibrium along an inclined plane. So in an exam, you should be able to answer such questions. Of course, they will always be very, very easy questions for your level. Let's now talk about equilibrium of suspended objects. I said in lesson 5, we shall talk about equilibrium in more details. So let's consider equilibrium of suspended objects. Remember, for an object to be in equilibrium, two conditions must be fulfilled. We mentioned them under moments. One, the resultant force or the net force on the body must be 0. And two, we mentioned that the net moment or the net torque on the body about any point must also be 0. So we're going to consider an example where we have an object that has been suspended. So the object in the diagram below has a mass of 40 kilograms. We are going to calculate the magnitude of the tensions T1 and T2 in the supporting wire. So we have a body which has been suspended by two wires, wire 1 and wire 2. Wire 1 is making an angle of 30 degrees to the vertical, and wire 2 is making an angle of 80 degrees to the vertical. And we want to find T1 and T2 if this object is in equilibrium. Of course, by the time an object rests like this, it is already in equilibrium. So there are two things which we can do here. One, we may easily, because many students prefer to use horizontal forces, or you can try to modify this diagram to you can try to modify this diagram to your advantage, either drawing a horizontal line or drawing a vertical line. So if I draw a vertical line, this angle is also going to be 30 degrees. This angle is also going to be 80 degrees because they are corresponding angles. So if this is 80, if I draw a vertical line, this will be 80. This will be 30. So we have a mass of 40 kilograms. So the weight is going to be the weight here is going to be 40 times g. So the weight here is going to be 40 times 9.81. So I'll come up with a simple diagram for the forces acting. So I have this horizontal, I have this line here. So there is tension in this wire here. Of course, tension always points away from the object. So I'll call the tension here to be T2, and I'll draw this line also. And I'll say the tension here is going to be T1. These are not drawn to scale. So this is 30 degrees and this is 80 degrees. If you want, you can use these angles with the horizontal, where this could be 10 degrees, and this would be 60 degrees, depending on which angle you want to use or which angle is easier for you to use. So there are two ways of solving this question. I will start with the simplest, which is resolving. If this is in equilibrium, then the resultant force should be zero. So by the way, there is a force acting downwards here, which is 40 times 9.81 newtons. So for equilibrium, it means the forces acting in opposite directions should be equal and should therefore cancel out each other. So using that principle, we can try to find T1 and T2. So if I resolve in the horizontal, I'm going to use the angles which were given in the diagram, such as 80 and 30. If I resolve T1 in the horizontal using 30, because I'm resolving to the horizontal, yet the angle given is with the vertical, it means in the horizontal it is sine, in the vertical it is cos. So in the horizontal we have T1 sine of 30. By the way, this is the same as T1 cos of 60. Should be equal to, because T1 sine 30 points to the left, T2 sine 80 points to the right. So this should be equal to T2 sine of 80. I'm saying that this is the same as T1 cos of 60 would be the same as T2 cos of 10 degrees. It is the same thing, so you choose one of these equations. Then when I resolve in the vertical, T1 in the vertical points upwards and T2 in the vertical points upwards. So the sum of those two will give us the weight downwards for equilibrium, because the resultant force must be zero even in the vertical. So we have T1, because in the horizontal it was sine, it means in the vertical it is cos. So it will be T1 cos of 30 plus T2 cos of 80 is equal to 40 times 9.81. So this is going to be my second equation. So it depends on what you want to do. You can modify equation number 1 and substitute it into equation number 2. So from equation number 1, T1 is going to be equal to T2 sine of 80 divided by sine of 30. So I'm going to substitute for T1 in the second equation. So I'll say T2 sine of 80 divided by sine of 30 times cos of 30 plus T2 cos of 80 is equal to, so let me see, 40 times 9.81 is equal to 392.4. Okay, so I must make T2 the subject, so I'll factor out T2 into brackets. I have sine of 80 cos of 30 divided by sine of 30 plus cos of 80. this is going to be equal to 392.4. So I'm just going to press my calculator and simplify the bracket. So I have sine of 80 times the cos of 30 divided by the sine of 30 plus the cos of 80. So the bracket is approximately 1.879. So I'll just divide the other side because I must make t to the subject. So it is 392.4 divided by the bracket. So I'll say 392.4 divided by the answer in the brackets. So this is giving me T2 as 208.8 or 0.79 if you want more significant figures, but this is approximately 209 newtons. Then if I want to find T1, therefore, to find T1, I will go back and substitute in one of the equations. So T1 is going to be T2, which is 208.79 sine of 80 divided by sine of 30. So 208.79 sine of 80 divided by sine of 30. So this gives us 411.24 newtons, or you can write approximately 411 newtons. So this is from calculation or from resolving. So we have used resolving to find the resultant, or to find T1 and T2. That is for resolving. By the way, we can also do this using a scale, but of course here you must be able to choose the best scale. Because G is 9.81, it may be very hard for you to choose a scale. Alternatively, this can be obtained by using a vector triangle. You can draw it to scale, or you can use a calculation. You can use mathematical principles to find the resultant. But since G is 9.81, if they had given us a good value of weight, we could easily find a scale and we just draw this to scale. However, if you are to choose a scale, still you must have a sketch. So I have to give you a hint on the sketch of the vector triangle. So remember, vector triangles, you must draw the vectors to scale. I mean, you must draw vectors head to tail. So there is a force acting vertically downwards, which is the weight. So I'll draw a vector vertically downwards, that is the weight. Then on the head of this, I must draw a vector which makes an angle 30 degrees with that weight which is acting downwards. So I have to draw this vector here, which makes an angle of 30 degrees to the vertical. That's why I need to find these angles. Then I have a vector which, when I take it backwards, this is T2. Remember, this is T1. When I take T2 backwards, it makes an angle. This angle is 80 degrees. So when I take this one backwards, it makes an angle of 80 degrees with the vertical. So I'll draw another vector here, which makes an angle of 80 degrees with the vertical. So the arrow is in that direction, and that is going to be T2. Of course, you must draw something where the lines are parallel, perfectly parallel. Maybe I should first erase this, because I want this line to be perfectly parallel with the wire. So this is what we call a vector triangle. And in one of the lessons, we said if three vectors are joined head to tail and they form a closed triangle, this implies that the body is in equilibrium. So if we could find a scale for this, we could just we could just draw a vertical line whose length is represented by a certain scale, and then we measure off 80 degrees from the vertical. We measure off 30 degrees from the vertical, and these lines will naturally meet on their own. Those lines would naturally meet on their own. And when they meet, we just measure the distance from here up to here times the scale. We measure the distance from here up to here times the scale. Those will be the values of T1 and T2, as simple as that. You can watch more of this in the solved past paper questions. Okay, so the answers, I think the answers are correct. Okay, example number 2. A load of 26 kilograms is supported in equilibrium by 2 ropes inclined at 30 degrees and 60 degrees to the horizontal. So let me draw the horizontal here, and we have 2 ropes. One is inclined at 30 degrees. These are not drawn to scale. Let this be 60 degrees. The other one is going to be 30 degrees to the horizontal. And there is an object here which is supported. So there is a force here which is going to be 26 times 9.81. That is the weight here. So there's a vertical force which is acting downwards. That is 26 times 9.81. If the acceleration due to gravity is assumed to be 9.81, find the tension in each rope. So there is tension, which tension always acts away from the object. So let this be T1 and let this be T2. Okay, so we're now going to find T1 and T2. I'll just use resolving because we are using G as 9.81. The product of 26 times 9.81 will make it hard for us to find the scale. But if you want to use a scale diagram, you can visit the solved past paper questions and see how that is done in more details. So using resolving, I'm going to resolve T1 and T2 in the horizontal. They point in opposite directions. So I have T1 cos of 30 is going to be equal to T2 cos of 60, which means T1 is going to be equal to T2 cos 60 divided by cos of 30. If you're a good mathematician, I think cos 60 is the same as sine 30. Cos 60 is a half. That's what I think. Cos 60 is a half, and cos 30 is the same as root 3 over 2, I think. Cos 30 is root 3 over 2. That's what I think. So it means we can say T1 is going to be equal to T2 times a half divided by root 3 over 2, which is the same as, I think this is the same as T2 divided by root 3. I think that is the same as T2 divided by root 3. So that is T1. T1 is the same as T2 divided by root of 3. Okay. Then we can consider the vertical. Resolving vertical, we have T1 sine of 30 plus T2 sine of 60 should be equal to the weight downwards, which is equal to 26 times 9.81. Okay, so when remember sine 30 is a half. Sine 30 is a half. So I have the T1 times a half, that is T1 over 2, plus T2 sine 60 is the same as cos 30. So this is going to be root 3 over 2. Is going to be 26 times 9.81. Okay, so I can now do substitution. I can remove T1 and I put T1 as T2 over root 3. So I can say T2 over 2 root 3 plus T2 root 3 over 2 is equal to 26 times 9.81. You can use any mathematics you know if you don't want to use these ratios of common angles. So I can multiply everything by 2 root 2. So I remain with the T2 plus, I'm multiplying everything by T root 2 root 2. So here the 2 cancels, root 2 times, root 3 times root 3 is going to become 3 T2. Here I'm multiplying, remember I'm multiplying everything by 2 root 3. So this is 26 times 9.81 times 2 root 3. So it means T2 is going to be equal to 26 times 9.81 times 2 root 3 divided by 4. So I'll just press my calculator. 26 times 9.81 times 2 root 3 divided by 4. So I'm finding T2 as 220 or 221 to 3 significant figures, 221 newtons. 221 newtons. Okay. I think this one gives you 225 point something newtons. Yeah, I think this was calculated using G as 10 instead of 9.81. So I'm getting 221 newtons as T2, then T1 therefore will be equal to T2 divided by root of 3. So that is 221 divided by root of 3. 221 divided by root 3, which is, this is going to be 127.6 or approximately 100 to two significant figures is 130 newtons. But I'm assuming they calculated these values using G as 10. Okay, so these are going to be the values for T1 and T2 by resolving. Some students also use another method of mathematics. I think they use Pascal's triangle. I don't know whether it is called, not Pascal's triangle, but there's another method which students use to solve that, which involves ratios of the angles and the sides and the forces. I think that is, they use sine rule, but there's another method which students use. I don't know how to use that because me, I'm not a mathematician. Okay. So as an assignment, you can check the answers by scale. If you use a scale, it is better you use G as 10. If you want to check with the scale, use G as 10 meters per second squared, so that choosing a scale is easier for you. In an exam where you are supposed to use a scale, the examiner will give you the force instead of the mass, because it will give you a force whose scale is easier to choose. Example 3, a particle of weight 16 newtons is attached to one end of an inelastic string whose other end is fixed. The particle is pulled at one side by a horizontal force until the string is taut and until the string makes an angle of 30 degrees with the vertical. Find the magnitude of the horizontal force and the tension in the horizontal string. So there's a particle, I'll sketch a diagram here, whose weight is 16 newtons. It is attached to one end of an elastic string whose other end is fixed. The particle is pulled at one side by a horizontal force. So there's a horizontal force, which we are going to call F. Until the string makes an angle of 30 degrees with the vertical. So it is supported somewhere. So it is pulled until it makes an angle with a vertical of 30 degrees. So there's tension here. So I think that is a sketch. Find the magnitude of the horizontal force. Since they have given us a force in newtons, I'm going to use both methods. I'll use the one for resolving and I'll use one for scale. So I'll just extrapolate this, or I draw a vertical line here. So this angle is going to be also 30 degrees. So resolving in the horizontal, we have that t to the left, it will be t sine of 30 should be equal to the force F. In the horizontal, there are two forces acting, t sine 30 and F. Then in the vertical, we have t cos of 30 will act upwards, and this should be equal to the weight of 16 newtons. So the question is find the magnitude of the horizontal force and the tension. So for the tension to be just 16 divided by cos of 30. So 16 divided by cos of 30. So this is 18.5. Then for F, of course, F can be found in two ways. Even if I don't know T, I can still find F. I can say F divided by 16 is equal to T sine of 30 divided by T cos of 30, where T cancels out. So I can say F is equal to 16 tan, because sine 30 over cos 30 is tan. So that would be tan of 30. So that is going to be 16 tan of 30, which would be 9.24 or 9.2 newtons. Alternatively, you can get the tension of 18.5 and substitute in the first equation, which has F. So method 2, I'm going to choose, let's say, I'm going to select 1 centimeter represent 4 newtons, I think. Let 1 centimeter represent 4 newtons. So it means for 16 newtons, I'm going to measure 4 centimeters in the vertical. So I'll draw a vertical line, but of course, before I do that, I must draw a vector triangle. So I have to draw a vector triangle. Where should I draw the vector triangle? Okay, I can draw it here. So I have a force which is acting vertically downwards, and this is 16 newtons. So this is going to be 16 newtons. Then I'll measure off an angle of 30 degrees. I'm just drawing a sketch first for the vector triangle head to tail. So I have, this is supposed to be 18 newtons, so it should be longer. So this angle is supposed to be 30 degrees. This is supposed to be the tension T. Then from here, you notice that F is horizontal, so I must draw a horizontal line. Remember, I am joining head to tail. So on the head of T, I must draw a horizontal line, and this is going to be F. So this must make an angle of 90 degrees with the vertical. So I'm now going to draw this to scale. So one, I'll start by drawing a vertical line. On this vertical line, I need 4 centimeters. So I have to measure off 4 centimeters. I need a reference point. So let me say I'm starting from this point here. So 4 centimeters stops around here. You can draw this on your book and to be interestingly good. Then I have to measure 30 degrees from the vertical. So here this is 16 newtons, because 4 centimeters is representing 16 newtons. Then I have to measure an angle of 30 degrees from the vertical at the bottom here. So with your 0 along the vertical on the top, from 0 to 30, I think that is around here. So 30, I'll draw 30 degrees. 30 is around here. Why does this always come when I'm drawing? Okay, so I've drawn an angle of 30 degrees from the vertical. You can measure this angle perfectly, but should be 30 degrees. Then all that remains is to draw a horizontal line where the 4 centimeters ended, because F is acting in the horizontal. So I'm drawing a horizontal line here. So I draw a horizontal line. The 4 centimeters stopped here, so I draw a horizontal line. That will be F, and this is going to be T. This must make 90 degrees with that because it was perfectly horizontal. So the next thing is just to measure the length. To find T, I must measure the length representing T from the graph, from the diagram. So I'll measure an estimate. This is 4 point. I'm getting 4.56. So I'm getting 4.6. Actually it is 4.7. So I'm getting T as 4.7 centimeters, but remember each centimeter is representing 4 newtons, so this is times 4. So 4.7 times 4, this is giving me 18.8 newtons. Then I also, to find F, I just measure the length representing F. And this is 2.5 exactly. So I'm getting 2.5 centimeters times the length times 4, because 1 centimeter represents 4 newtons. So I think this is 10, 2.5 times 4. This is approximately 10 newtons. So these are the values I would get from a scale diagram. Of course, they cannot be very exactly the same, but they would be a little bit close. Okay. So that is how we use the scale diagram to find those vectors or those values. A uniform rod AB is attached to a vertical wall at A. The rod is held horizontally by a string attached at B and point C, as shown below. The angle between the rod and the string at B is 50 degrees. The rod has a length 1.2 meters and weight 8.5 newtons. An object of mass m is hung from the rod at B. The tension T in the string is 30 newtons. Use the resolution, in other words, use the resolution of forces to calculate the vertical component of T. Use the principle of moments and take moments about A to show that the weight of the object is 19. Hence, determine the mass m of the object. Use the concept of equilibrium to explain why a force must act on the rod at A. Okay, so I'm going to use the resolution of forces to calculate the vertical component of T. So resolving T vertically upwards using the angle 50, this is going to be T sine of 50. The weight is 8.5. The weight is 8.5 newtons. And the mass here is m. The angle between the rod and the string is 50. The length is 1.2. The weight 8.5 newtons. An object of mass m is hung from the rod at B. The tension T is 30, so this is 30. So it means the answer here is going to be just 30 sine of 50. 30 sine 50. So that is going to be 22.9. This is approximately 23 newtons. So that is the component, the vertical component. So T sine third, this is equal to 23 newtons. And that means this component has a moment in that direction about point A. And that is going to be anti-clockwise. The weight has clockwise moment. M also has clockwise moment. So I'm first of all going to find the weight here instead of finding the M. Use the principle of moments and take moments about A to show that the weight of the object is 19. So let's say the weight is W. So using the principle of moments, sum of clockwise moments is going to be W times the perpendicular distance, which is 1.2, plus, because 8.5 is the weight of the rod, it is acting at the midpoint. So this distance is going to be 0.6, half of 1.2. So I will say this is equal to 8.5 times 0.6. This should be equal to the tension, which is 23, times the perpendicular distance, which is 1.2. The horizontal component of the tension acts through point A. It will point in that direction. So it has no perpendicular distance because its line of action will go through the pivot. So it has no perpendicular distance. So this means I can find W as being equal to 23 times 1.2 minus 8.5 times 0.6, and then I divide this by 1.2. So this is giving me 18.75, which is approximately 19 newtons as required. Hence, determine the mass M. Of course, if I have the weight, then the mass is equal to the weight divided by G. So that is going to be 19 divided by 9.81. So this is approximately 2.0 or 1.9. 19 divided by 9.81. This is 1.9 kilograms. So M is 1.9 kilograms. Use the concept of equilibrium to explain why a force must act on the rod at A. Note that the resultant force must be equal to 0. Number 1, let's first sum up 8.5 plus the weight and see if it is equal to 23. So total forces downwards is 8.5 plus 19. That is 27. So we have already that so that means there must be a force here which acts vertically upwards. So total force downwards equals to 8.5 plus 19, which is approximately 27.5 newtons. So it is not equal to the vertical component of it is not equal to the vertical component of the tension, which is 23. Therefore, there must be a force. There must be a force on the rod at A. So another force on the rod at A must act upwards for equilibrium to occur, for equilibrium to happen. And if you want to find the force upwards, you can say 27.5 minus 23. So there's a force here whose value is going to be 27.5 minus 23, which is approximately 4.5 newtons upwards. Of course, the component of T cos or T sine theta is going to be balanced by a force which is exerted on the rod in the opposite direction, which should also be T sine theta, which should also be equal in magnitude. The component of T in the horizontal is balanced by the force exerted on the rod in the horizontal from the wall, which should be equal but opposite. Okay, I hope there are answers here. I don't know if they are correct. So for equilibrium, I said the resultant force and the resultant moment must be zero. The upward force is not equal to the downward force. The horizontal component of T is not balanced by the forces shown, thus a force must act on the rod at A to ensure equilibrium. This is supposed to be the vertical. The vertical component of T is not balanced by the forces shown. Thus, there must be another force to ensure that equilibrium is achieved. Okay, so of course, there is also a horizontal force, but I want to concentrate on the vertical force. Self-check. A rigid rod PQ has length 2 meters. A body of mass 12 kilograms hangs from P and another body of mass 8 kilograms hangs from Q. The system is suspended from point A of the rod, where A is x meters from Q and is in equilibrium. With the rod horizontal, find the value of x. I'll just draw a sketch here, maybe for your reference, to give you a hint. Let's have a rod PQ. It is 2 meters. A body of mass 12 kilograms hangs from P. So here there is a body of mass 12 kilograms. And another body of mass 8 kilograms hangs from Q. So here there is another body of mass 8 kilograms. The system is suspended from a point A of the rod where A is x meters from Q. So let's say this is the pivot A and A is x meters from Q and is in equilibrium with the rod horizontal. Find the value of x. Of course, it means this distance here is going to be, because the length was 2 meters, this is going to be 2 minus x. So just consider moments. I may not even change the mass to weight. I'll simply say, taking moments about the pivot, I know that x times 8 should be equal to 2 minus x times 12. So 8x is going to be equal to 24 minus 12x. So in other words, 20x is equal to 24. So I just divide to find x. 24 divided by 20, which gives you x as 1.2. I think that is the units are in meters. So I think that is easy. A sphere of weight 40 newtons and radius 30 centimeters rests against a smooth vertical wall. The sphere is supported in this position by a string of length 20 centimeters attached to a point on the sphere and to a point on the wall. Find the tension in the string, the reaction to the wall. Okay, I will still give a hint here, but I don't have enough space, so I'll just draw in this text. So let this be the wall, and a sphere is resting against the wall. So I will draw a sphere here, and it is supported by a string. The radius of the radius is 30 centimeters. The length of the string is 20. So this is 20 plus the radius, which is 30 up to the center. Then I'll draw a horizontal line through this. So there is tension here. There is normal reaction from the wall. So I'll call this reaction R from the wall. And there's also weight acting vertically downwards. So those are the forces acting. There is tension. The sphere is 20 centimeters. The radius is 30 centimeters. There is weight of the sphere. There is normal reaction. So the question is find the tension in the string. So they have not given us the angle, but they say the weight is 40 newtons. The radius is 30, smooth wall, there is no friction. The sphere is supported in this position by a string of length 20. Because the radius is 30, I can find the angle. So this angle here, if I consider a triangle, because the radius is 30, if I try to consider a triangle and this angle is theta, opposite hypotenuse, that is sine. So sine of theta is equal to the opposite, which is 30, divided by hypotenuse, which is 20 plus 30, which is 50. So this means the theta is equal to sine inverse theta is sine inverse of 30 divided by 50. So theta is approximately, I would just take 37 degrees. So that is theta. So that means this angle with the vertical is 37 degrees. So if I want to find, for example, t, I have to resolve t to the vertical, and it will be t sine, no, t cos of 37. So t cos of 37 is the same as the weight, which is 40 newtons. So I'll say 40 divided by cos of 37. So this means t is equal to 50, approximately 50.1. So this one means t is equal to 50.1 newtons. You can verify that. If I want a normal reaction, I have to resolve t to the horizontal. So t in the horizontal is going to be t sine of 37, which should be equal to r, because t sine 37 points to the left to balance the normal reaction r. But remember, t is 50.1, so it means r is just going to be 50.1 sine of 37. Which I think these answers are correct. Of course, it acts at an angle of 90 degrees to the wall. The normal reaction, it is called normal reaction, so it acts at 90 degrees to the wall. Yeah, because I don't have space, I had to write in these words, so you should bear with that. A beam of mass 20 kilograms and length 2 meters is attached to A, which is a point on a vertical wall. The beam is maintained in a horizontal position by means of a chain attached to a point in a wall, 1.5 meters vertically above A. If the beam carries a load of 10 kilograms at a point 1.5 meters from A, calculate the tension in the chain. I must solve this for some students. I will use the second page. Before we talk about ladder problems, I want to solve that question. I will sketch a diagram. So the beam is of mass 20 kilograms and length was, I think, 2 meters attached to A on a vertical wall. So I'll start by drawing a vertical wall here. So the beam is attached somewhere here. The length of the beam is 2 meters and it is attached at point A. So this is point A, at which is a point on the vertical. The beam was, I think, maintained horizontal by means of a chain attached to a point 1.5 meters vertically above A. So this distance was given as 1.5 meters. So the other end is at a point of 1.5 meters above point A. So that is the chain. If the beam carries a load of 10 kilograms at a point. The beam was carrying a mass of 10 kilograms at a point 1.5 meters from A. So at 1.5 meters from A, the beam was carrying a mass of 10 kilograms. Then we were to calculate the tension. So there is tension here. Okay, so I think if I've sketched this now, this becomes easy. Calculate the tension. They gave us the mass of the beam. Of course, the mass is going to act at the center of the beam at 1 meter. So this is going to be 1 meter. So the weight of the beam is going to be 20 times g. The mass here is going to be 10 times g. And the distance of the mass from the beam, I think it was given as 1.5. I mean, from the point it was given as 1.5 meters. So all you need is to find the angle. Since the horizontal is 2 meters, the vertical is 1.5, you can find this angle theta using, I think that is cos. Then that angle is going to be the same as the angle here because you want to resolve t to find the t cos of theta. And theta, adjacent hypotenuse, that is cos. Cos equals cos theta is 1.5 divided by 2. So this gives you the angle theta. So the angle theta is going to be cos inverse 1.5 divided by 2. Cos theta is adjacent. No, that is not cos. Adjacent, opposite adjacent, that is tan, not cos. Tan theta. Tan theta is opposite of adjacent, not cos. Because 2 is in the opposite and 1.5 is the adjacent. So this is 2 over 1.5. So shift tan inverse of 2 divided by 1.5. So it means theta is going to be 53 degrees. So this is 53, this will also be 53 degrees. So if I want to find, they wanted us to find t. So I can find t by just taking moments about point A. I can't add the forces upwards because there's another force here. There could be another force at A acting upwards, which I don't know, but I can take moments because the force at A will not have a moment about A. So I'll say T cos of 53. T cos 53 times the perpendicular distance, which is 2 meters. That is going to cause anticlockwise, should be equal to, this will cause clockwise, the other will also cause clockwise. So it is going to be equal to 20 times 9.81. That is force. Perpendicular distance is 1 meter plus 10 times 9.81 times the perpendicular distance, which is 1.5. This is a total sum of clockwise moments. So I'm just going to press my calculator to find t. So 20 times 9.81 then times 1 plus 10 times 9.81 times 1.5. Then I divide this by 2. I divide this by cos of 53. So the T is going to be 285 newtons. You can try to verify that. I could make some errors, but I think that is correct. So the tension could be approximately 285 newtons. Okay, so that could be the solution to the last example before ladder problem. So I'm going to delete this. You can pause the video and go through it again, but I need this space, I think. Okay, so let's consider ladder problems under equilibrium still. So we are going to consider a beam resting against a smooth wall on a rough floor. The forces acting on the beam, or they call it the ladder, because these are ladder problems. You can call it a ladder or a beam. So the forces acting are going to be at every point of contact, there's a normal reaction force. So we have a normal reaction at the wall. We have a normal reaction here. If the wall is smooth, there is no friction. The wall is smooth, so there's no friction. The ground is rough, so there's friction. The ladder is most likely going to slide downwards for the wall as it moves away from the wall in the horizontal. So because it tends to move in that direction, then it means the frictional force must be towards the wall. That's why there's an arrow pointing towards the wall. So if it is the only possible way of the ladder to slide is for it to slide away from the wall and downwards. If it slides downwards and away from the wall, it means the friction should be towards the wall to oppose the sliding. The friction force will be towards the wall to avoid the sliding. So, one important thing we need to note is that friction can only exist where the surface is rough. That's why we are only putting friction on the ground, on the rough floor. Only where there is a rough surface, that's where we expect friction to act. If they had told us that the surface is smooth, then we would not talk about friction in that case. The friction force points towards the wall because there is only a possibility of the ladder sliding away from the wall. That's why the friction is pointing towards the wall. By the way, if the wall was also rough, then there would also be friction between the wall and the ladder. Because the ladder can, or the beam can only slide downwards, the friction on the wall would be upwards if the surface of the wall was also rough. This would point upwards since the ladder would slide downwards against the wall. But since the wall is smooth, we don't expect to talk about friction in such a case or in such a scenario. So how would we resolve forces around the ladder? I want you to notice the forces which are acting on the ladder or on the beam which is resting on the wall and on the floor. At every point of contact, there is a normal forces. There are normal forces. There is normal reaction force at the point of contact. There's a normal force at the point of contact. Of course, the weight of the beam acts vertically downwards, as shown by this letter W. Because the ladder is most likely going to slide to the right-hand side, the frictional force acts to the left-hand side. Remember, for equilibrium, the resultant force in any direction should be zero, and the resultant moment about any point or about the same point should be zero. So, if we consider the same ladder, therefore, for static equilibrium, or if the ladder is in static equilibrium, the following conditions must be applied. Number one, the sum of forces in the horizontal should be equal to zero. In other words, the resultant force in the horizontal is zero. That's why I'm saying R to the right-hand side should balance with F to the left-hand side. That's why I'm saying R minus FR is equal to zero, or precisely R is equal to the frictional force in the horizontal. Then in the vertical, they should also be equal, they should also balance. So the weight downwards should be equal to the normal reaction force upwards. That's why I'm saying N minus W should be equal to zero, or simply N equals to W. Also, we should be able to take moments about any point. For example, if N and FR are not known, the best thing would be to take moments about point A. Why? Because we can eliminate N and FR so that we can easily find R. And if we have found R, it means we have found FR, because FR is the same as R. So R times perpendicular distance of R from A minus W times perpendicular distance of W from A should be equal to zero, simply because N and FR will not have any moment. By the way, you can also take moments about B. But of course, if we take moments about B, the friction will not have any moment. N would pull the beam in that direction. So it means N is acting anti-clockwise. W about B is going to act clockwise. R will be acting clockwise. However, the problem is that you'll have so many unknowns. So you can take moments about B and C, but we choose a point with many unknowns so that we can eliminate them first. That's why choosing A, if N and FR are not known, choosing A eliminates N and FR first. And I only remain with R. So this is because all forces at the point where the moments are taken have zero moment, since they are perpendicular distance of their lines of action from the particular point will be zero. So if I take moments about A, the line of action of FR goes through A, its moment is zero. The line of action of N goes through A, its moment is zero. So I have literally eliminated N and FR. So I only remain with the moment of R and the weight. If the weight is known, then R can easily be found if I take moments about A. So let's put this in an example to fully understand this. So the figure shows a free body diagram. Of course, a free body diagram is a diagram which shows only the forces acting on the object. So a free body force diagram for a ladder resting against a smooth wall. The wall is smooth, there is no friction. The only forces acting is the normal reaction force. Determine the forces R1, R2, and frictional force Fr. So remember, for equilibrium, the forces in both opposite directions should be equal. So I know that R1 must be the same as frictional force Fr. If I can find R1, it means I have found Fr. And I should also notice that the weight W should be equal to the normal reaction R2. So I don't need to find R2 again because the weight is 200 newtons. So R2 is going to be 200 newtons for equilibrium to happen in the vertical. So the only way I can find, or I can easily find R1 is by taking moments about A. So I'll say moments about A. So if I take moments about A, it means R2 and FR will not have moments. W will pull the beam clockwise as R1 pulls the beam anti-clockwise. The only thing we need is the perpendicular distance of the line of action of R1 from A. So this is the perpendicular distance, the length of the line from the line of action, which makes 90 degrees if drawn from point A, which is 3 meters. So this distance here is 3 meters from point A. So taking moments about A, we have R1 times its perpendicular distance from A, which is going to be 3 meters. I know students cannot see that is 3 meters, but I'm saying perpendicular distance is the length of the line which makes 90 degrees with the line of action of the force. And that line is drawn from the point where we are taking moments. The length of the line from the point where we are taking moments to the line of action of the force. But that line we have drawn makes 90 degrees with the line of action of the force. And I'm saying this length here is the same as this one here. So R1 times 3 should be equal to, because R1 times 3 is anti-clockwise, should be equal to W, which is 200, times the perpendicular distance, which has been given as 1.2 meters. So R1 is going to be equal to, so 200 times 1.2 meters divided by 3. So R1 is equal to 80 newtons, which means that the frictional force is going to be 80 newtons. So R1 is 80, FR is 80, R2 is going to be 200 newtons. As simple as that. A ladder of length 2A is leaning against a wall which is smooth. A ladder of length 2A is leaning against a wall which is smooth. So the wall is smooth. I can sketch this here. So the wall is smooth, so I'll draw the ladder. Maybe I can put here the ground. And resting on a rough floor, so there is friction. Friction must be acting in this direction here. Friction if the ladder has a weight of 18 newtons, acting at a point a third. So the length of the ladder is 2a. That is the total length. But its weight acts at a third from the foot. So 1/3 of 2a is where the weight acts. So let me put here 18 newtons. 18 newtons is acting at a distance of 1/3 of 2a. A third of 2a. So it means this distance is going to be 2a divided by 3 from the bottom to where the weight is acting. It is 2a times 2a over 3. Okay, find the normal reaction. Find the normal reaction on the wall and the friction force, assume the ladder makes an angle of 30 degrees with the wall. So they are saying it makes an angle of 30 degrees. This is 30 degrees with the wall. If the easiest angle to use is this one, remember this is 90, so this is 60 degrees. Okay, so we are just going to take moments. I think that is the easiest method we are going to use here. Taking moments. Let's take moments at the ground here. Let's take moments at point A. So assume the ladder makes an angle of 30 degrees with the wall. That means the angle between the ladder and the ground is 60 degrees. So the weight about this point here is going to cause an anticlockwise moment. But of course, there are forces. There is no more reaction here. There is no more reaction here. So I'll call this one N1, N2. So if I take moments about A. So N1 has no moments. Friction force will also have no moments. So I can find N2 has no moments and friction force has no moments. So I can find N1. But remember, N1 is going to be equal to the frictional force. And remember, N2 is equal to the weight. Okay. So taking moments about A, the sum of anticlockwise moments, we have to find the perpendicular distances. That is the hardest thing for students, finding the perpendicular distance. So the perpendicular distance of the weight from the point we are taking moment is this length here. And this distance I will call it D. We have this is cos, this is the angle 60. The distance is this in the adjacent. We have the distance from this point up to this point, which is going to be the hypotenuse. So the hypotenuse is 2a over 3. So the distance D is going to be got from adjacent, that is cos of 60 is equal to D over the hypotenuse, which is 2a over 3. So D is going to be 2a over 3 cos of 60. So taking moments about A, for the weight, it is going to be 18 times the perpendicular distance, which is 2a over 3 cos of 60, should be equal to, that was anticlockwise. Clockwise moment is given by N1. So it is going to give us N1 times the perpendicular distance of N1. So for N1, the perpendicular distance is the same as this distance here. Because we draw the line of action like this, its perpendicular distance from where we are taking moments is the vertical line with the horizontal ground, which makes 90 degrees, which is the same as the other one. And remember, this is in the opposite. We have the hypotenuse. If I use 60, the perpendicular distance in that case, let me call it x. This distance here is perpendicular distance for N1 from A. X is going to be equal to, okay, opposite hypotenuse, that is sine. So I will say sine of 60 is equal to the opposite over the hypotenuse, which is 2a. So x is 2a sine of 60. So this is N1 times 2a sine of 60. So what is N1? A cancels out, 2a cancels out. 18, so N1 is going to be equal to 18 divided by 3, that is 6 cos of 60, divided by sine of 60. So 6 cos 60 divided by sine of 60. So N1 is going to be 3.5 newtons. That means the frictional force is 3.5 newtons. Then we have to find what is the other one. Assume the ladder makes an angle of 30. Find the normal reaction on the wall, that is N1, and the frictional force. Of course, the normal reaction on the wall is the same as the frictional force. So I think that is all. I think that should be the end. I don't know whether this should be the end of force, density, and pressure. So this should be the end of force, density, and pressure.